we need to change it to Röntgen, Kelvin? The answer is we can keep it as is, as long as the unit on the top and the unit on the bottom are the same. Okay? Because look, even if I use Celsius, okay, the unit will cancel. If I use Fahrenheit, the unit will cancel, right? And it's not absolute value, it's a difference. Okay? It's an increment of the temperature, so it's fine. And the ratio for Celsius over Celsius is unitless. The ratio for Fahrenheit over Fahrenheit is unitless. Okay? Good? So that is potential question for the exams, but it could be something else. Okay? Alright, let's do any question on heat transfer? How much do you want to buy with the pipe in Texas? 42 inches, right? Okay. Alright, flow assurance. We will go through it only on the part that is important. There are many things that is important, okay? Flow assurance is a big topic, and I have this material from Hausa and add some more from the book or other reference that I have. Flow assurance is production operation that generate a reliable, manageable, and profitable flow of fluid from reservoir to the cell point. Okay, that is the definition from protocol for it. Okay, we need to have the way that is very profitable, okay, manageable. We have to move fluid safely. What prevents the safe operation? Hydrate can prevent the safe operation because hydrate block the pipe. Wax deposit in the pipe. Asphaltene happen in the reservoir, so it's not good, right? We can have asphaltene precipitation and block the pore space in the reservoir. So we need to know the mechanism that cause this thing to happen. Flow assurance, we have concern on flow assurance mostly offshore, but onshore we also have that problem too. Okay, this is a location. We have long subsea pipeline too. Okay. Can block the pipe and stop the flow. Okay, and removal of hydrate can be dangerous. Okay, removal of hydrate can be dangerous. We will talk a little bit more when we are there. So this example shows that loss of production for the subsea pipeline is significant. I mean, it's $1.2 million. Okay, it can be $25 million, or it may be more. Maybe more. What is more? Last more company in UK abandoned the whole platform at the cost of $100 million due to wax deposit problem. Okay, but that's of course a long time ago. But they have to abandon the whole platform. Just we have wax deposit. Okay, that's the magnitude of the problem. Okay, when we have wax deposition, what people do is clean the pipe. How do they clean the pipe? They put a pig that they call a pig. So it is a device that can block the pipe partially. We put that pig into the pipe and we use the pressure of the fluid by itself to push the pig forward. Okay? When the pig move forward by the force of the flow itself. When the pig move forward, it will scrape any deposit with it. Okay, if we have the deposit on the pipe, but so let's say deposit is look like this. That is a deposit. So when the pig come hit it, pig will like crash it and remove it. Okay, that is the purpose of putting pig in. So if we have a thick, okay, if we have thin deposit, okay, the deposit is thin. Okay, let me draw a pig. So there is a pig. We have a thin deposit. Deposit is very thin. In this case, no problem. Pig will scratch the deposit. Deposit come out and go along with the flow, and we take it out at the pig receiver. Pig going in at the pig launcher. If we have a thick deposit, what can happen for the thick deposit? Do you think it can get stuck? Pig will get there and doesn't move. It gets stuck. So when pig gets stuck, what do? We have the downtime, we have to flow back or something, okay? So we don't want pig to get stuck. Why do we have pig to get stuck? That is because we put the pig in, right? Many people say it's because we put the pig in, but flow assurance engineer will say we did not put the pig in enough. We don't put at enough frequency. Okay, if you put it in often, like I clean it often, it won't have time to get very thick. Okay, but if I clean it every month, okay, maybe it's too thick. Okay, so if you clean it every day, it will not have a chance to grow a strong deposit. Okay, the deposit, for example, wax will get thicker. Not only thicker, will be harder or more difficult to get removed. Okay, over time. So we should clean it often. There's a problem of cleaning often, okay? Look at this axis. Deferred revenue, $1 million per year versus picking frequency. If we pick at 7 days, if we pick at every 7 days, the operating cost is $25 million, okay, deferred revenue. Deferred revenue means it takes some time to put pig in a pig launcher, right, and take pig out to the pig receiver, so it slows down the production a little bit, and we have to pay the worker to do all that. So picking costs money. Okay? If we pick more, it costs more money. If we don't pick at all, it doesn't cost any money on picking, but it may cost the money on the whole pipeline because it's too thick to do to remove it. When they pick the wax deposit, if they don't know what is inside and they think it is hard, they just think that it is hard, they will use conservative approach. Conservative approach means step 1, inject the chemical in, okay, crystal modifier or paraffin inhibitor, just inject the paraffin inhibitor in, let it flow for a while, then put a soft pig. A soft pig can be foam pig, made of foam, just that. And sometimes foam pig go into the pipeline and never come out. They just go in there and disintegrate. Okay. After they do the foam pig, then they put a stronger pig in. Okay. But the diameter, instead of occupy the whole pipe, maybe less, maybe just this. Okay. So that it doesn't get stuck, and increase the strength of the pig gradually. Okay. Once they know that the pipeline is clean, how do they empirically determine the picking frequency? Number 1, they do day 1 picking. Okay, something come out. Do day 2 picking. The interval is 1 day, right? Hey, there's nothing come out. Okay, so next time we don't do every day, we do every 2 days. So when we do every 2 days, still nothing come out, then we do every 4 days. So it double the interval. Then we do every 8 days, every 16 days. Hey, at every 16 days, something come out. So they may stick with 16 days. That's how they empirically determine the picking frequency. Nevertheless, we don't want to know the picking frequency at the runtime, at the operating time. We want to know it in advance. This is because we need to know if the project is economically feasible or not. Because we know if we pick that many times, we will know the cost, right? Sometimes if we have to pick too much, it may not be cost effective. Okay? So they prefer to know the picking frequency ahead of time before the actual operation. But sometimes it cannot be done. Okay? This is a picture of each type of deposit. That is hydrate, wax, asphaltene, that's asphaltene, mineral scale, what they call scale deposit. And that is, what's that? I have to go have lunch. Okay, that's a net deposit. So that's a net deposit. That net deposit sometimes has in a separator, okay? Within all this deposit, what I need to know is the time scale. Hydrate form within 10 minutes, okay, 15 minutes, maybe half an hour. So could be 5 minutes. Hydrate form quick, okay? And when it forms, it blocks the pipe like that, very quick, okay? Hydrate form very quick. The time scale of wax can be, depending on where we are, the time scale of wax can be, most likely we're gonna say days. I mean 10 days, 15 days, it could be 1 day, but it's not like half an hour, no. Wax doesn't form within half an hour, this is wax deposition. So wax deposition can form, the time scale of wax is in the order of day, but the time scale of hydrate is in the order of minutes. Okay, that is there, maybe 10 days, 15 days, maybe 1 month, or we never have to pick at all. S14 is a little bit ambiguous. Okay, the way that wax form is due to heat loss. If we don't have heat loss, wax doesn't deposit. Okay, the way that scale form is we have to have some kind of salt in water phase, or when we have water phase and oil and we have salt, it can form. So we put scale inhibitor in hydrate form if we have free water phase and we have high temperature, high pressure, low temperature. Naphthalate form when it's kind of acid, when the pH is like low, we have a chance to form naphthalate. Other problem can be emulsion, corrosion, or high viscosity oil. High viscosity oil is one problem of the flow assurance because by definition, to assure that the flow will go from the reservoir to the cell pipe, if it is too heavy or it's too viscous, it doesn't flow. It doesn't flow economically. Okay? So we have several problems. We can have hydrate, and these problems have different time scale. We may have sand. All these things is a flow assurance problem. Another thing is about severe slugging. Severe slugging we show a little bit in the lab, but it's a little bit difficult to show. What happens is if we have double section connect to upper section, the low spot will have water accumulated. Okay, water stay at the low spot. Gas cannot go. So just water level go up, right? Gas accumulate over there. When gas have enough pressure, what happens when gas has enough pressure? It can get in. So when gas has enough pressure, gas can go into the vertical section, right? When gas go into the vertical section, it reduces the hydrostatic head in the vertical section. This accelerates the phenomenon. More gas come in. More gas come in, hydrostatic head reduce even more. So a lot more gas will come in. Eventually, the whole liquid column push to the top. Go to the separator and it's upset the separator. Okay, so they don't want serious slugging to happen. And this kind of problem, maybe we may have something else. For example, if someone gets drunk and have a gun, that is not a good combination. So on 2001, a person who gets drunk and have a gun accidentally or maybe on purpose shot the pipeline. And who knows, it's oil coming out a lot. This is a top bill. So 285 gallon spill and cost $15 million to this M is million, okay, to clean it. So we can have other problem. This is Trans-Alaska pipeline. Okay. So to assure that we have flow, we have to have the leak detection system, maybe to prevent the corrosion or something. Problem happen most of the time on the startup and shutdown. Okay, on the steady state, when it works already, problem is not quite likely. Most of the problem happen on the transient when we are about to start or we are about to stop. This example is for Block 60, 1989 problem when they try to fix the pipe. What happened is we have subsea pipeline. Okay, there's a leak at the bottom. Okay, there's a leak at the bottom. So when we have the leak, there's a communication between fluid inside and the sea level. Okay, and they try to install a pig receiver on the top to clean this. What do they think? They think, okay, we have the breakpoint, water coming in. We have a valve on the top, so that is a valve. Okay, we want to install some kind of pig launcher, pig receiver to do some operation to clean it. They have to cut the pipe to do some modification on the top. Okay. So what happens when they cut the pipe? Oh, let's cut it over there. Let's cut it over there. So when they cut it over there, option one, that the thing happened, the fluid over there coming out. And it becomes dry, and we install our equipment to do the repair. Okay? Do you think option one happened? No, it doesn't. Okay? Option two, the fluid everywhere over there go up and kill everyone. That's what happened, okay? Why is that? So it is about hydrostatic head, okay? When there's a leak, we cut it, maybe this is sea level. Okay, sea level. Maybe go back to this picture. So like in the lab, oil has lower density, right? Oil has lower density. Water has more density. So when we cut over here, we have the leak. Water in the sea is an infinitely large reservoir. So water from ocean keep going in. So this thing keep coming out, like that. So if I put a YouTube class in the subsea, and I have hole over here. So this allows water to keep coming in, right? It's a lot of water. So if I destabilize it, have a hole over here, fluid on the top doesn't coming out, but fluid from the bottom go up, like that. Okay? This happened, but they cannot prevent it because it's not slow. It happens so quick. What they believe to happen is serious locking. When they shut down the pipe, there's an air pocket over there. So that is the air pocket, right? So when all these liquid go over there on the vertical section, gas get into this part, right? When gas get into that part, what do you think happened? It reduces the hydrostatic head, like doing the gas lift. Okay, when the hydrostatic head get reduced, gas go in more, and a lot more can come in. It accelerates the process. This cause it happens so quick that they cannot close it. When they cannot close it, I think how many people died? Lost 7 lives. The extraction of the platform. Okay, so this is not going to happen. If we want to cut anything, don't cut below the safety valve. Cut above, even though we make mistake, we can close it. Or cut on the top when it's already dry because the fluid from the bottom can go up. Okay. That is the introduction for about transient phenomena for multi-phase flow. Okay. People use commercial software and run the commercial software to simulate what kind of danger that can happen during the transient operation. When we close the valve, open the valve, what is the pressure profile, what happened for the flow rate. So this has to be done during by using the simulation to ensure the safety operation. Okay, for the hydrate, we already know everything. Okay, the part that we may not emphasize that much is about inhibitor. Methanol shift the hydrate phase envelope. Therefore, methanol is considered as thermodynamic inhibitor. Okay, methanol is thermodynamic inhibitor. Konande? Okay, not here. Who else? Who else is missing? Schwann, Calvin, Schwann. Shavon, Schwann? Not here. Shavon. Not here, right? Okay. Just those two. So methanol is considered as thermodynamic inhibitor. Okay. There are three kinds of inhibitor for hydrate, and this could be an example. Okay. We have thermodynamic inhibitor. Thermodynamic inhibitor shift the hydrate phase in a law. Number two, kinetic inhibitor, it slow down or inhibit, prevent it from growing. Okay. And we have anti-agglomerant, they call AA. Anti-agglomerant allow it to form but doesn't get together, so it cannot block the pipe. This is the inhibitor that we use for hydrate. We skip all the structure. We talk about it, the experiment, of course, we skip. Let's talk about wax. So hydrate is mostly water and gas, right? Hydrate is a crystal structure of water and gas. Crystal structure of water that trap gas inside. Paraffin is mostly an alkane component. Okay, this is paraffin. It forms 3D structure network. We have two words. Number one is wax precipitation. Number two, wax deposition. Deposition means stick to the wall. Precipitation means change the phase and become solid. Okay, that is precipitation. When it precipitates, it doesn't mean that it deposits. Okay. The mechanism for wax deposition is not like solid wax attached to the wall. No, it's not like that. What they believe is the diffusion happens. Okay, the wax that dissolves in oil is responsible for wax deposition. The wax that already precipitated out in a solid phase doesn't responsible for wax depositions. So for wax deposition to happen, number one, they talk about here. Okay, let's talk about it. Okay, let's talk about the concept of wax appearance temperature. WAT, wax appearance temperature. This means the temperature below which wax crystals start to form or solidification of wax happen. Okay, wax becomes solid. If I heat it up, decrease the temperature, the first temperature that solid phase form, that is WAT. Okay. I decrease the temperature, it's cold now. We have a lot of wax, and I heat the temperature up again. The temperature at which everything dissolve wax, that called, or every wax disappear, that's called wax disappearance temperature. We have mismatch, okay, hysteresis. WDT, or wax disappearance temperature, is not the same as wax appearance temperature. Okay? Wax disappearance temperature is higher than wax appearance temperature. This means if I want to get rid of wax, I have to heat it up more than the point where it appears. Okay? I have to heat it up even more. Maybe when I decrease the temperature down, it starts to precipitate at 40 Celsius. But when I want to get rid of it, I have to go above 40 Celsius. Okay? So this shows me the amount of solid phase that being formed. So this is solid phase, solid weight fraction versus temperature. When I decrease the temperature, wax precipitate. Decrease the temperature, wax precipitate more and more and more and more. So temperature go down, wax precipitate more. Okay? Got it? Low temperature, more wax precipitate. High temperature, less wax precipitate. Above WAT, wax doesn't precipitate. It is so. Okay, the problem with wax precipitation is that, if the temperature is too low, it may not stick to the wall, but it gel, freeze everything. It stays in the pipe, it freezes everything, and it makes no movement. So this is gelation temperature, okay, of wax. Wax deposition happens because we have heat loss. In the pipeline, when we have heat loss, wall temperature will be colder. So the temperature of the wall is cold. The temperature inside is hot, right? So the temperature inside is hot, the temperature at wall is cold. So when the temperature at wall is cold, we have more wax precipitate at the wall and less wax precipitate in the middle. Do you agree? So this means in the middle we have more wax dissolved in liquid phase. At the wall we have less wax dissolved in the liquid phase. So concentration of wax in the middle is more than concentration of dissolved wax at the interface. Because of this concentration difference, this concentration gradient is a driving force for the dissolved wax to convectively have convective mass transfer toward the pipe wall. Okay. So in short, the middle of the pipe is hot. When it's hot, there's a lot more wax dissolved in at that location. At the wall, there's a little bit or less wax dissolved in because the temperature is lower. Because of this concentration difference, it causes wax to deposit. For wax to deposit, the wall temperature, the inner wall temperature has to be lower than WAT. Okay? The inner wall temperature has to be lower than WAT. Inner wall temperature has to be lower than WAT. The bulk fluid temperature doesn't need to be lower than WAT. It can be more than WAT. It can be less than WAT. The important thing is inner wall temperature. So the second one is the surface temperature. Okay, is lower than the bulk temperature. The temperature at the wall has to be lower than the temperature in the middle or in the bulk phase. So in the bulk phase, the temperature may be 40, the temperature at the wall may be 30. Okay, this is just a number. And WAT is 35 in this case. When there's a temperature difference, then we can have deposition. The third thing is the wall must have enough attraction to the deposit. If the wall is very extremely slippery, it doesn't deposit. But we don't have that kind of pipe material yet. We have it just in the lab. Okay. In practice, we just use carbon steel pipe and deposition can happen. Okay. You get the idea, right? Why wax deposit or how it deposits. Let's talk about something else. This is the etching of wax. There are a lot of things to talk about wax. This is a facility where they do the wax deposition test, use a flow loop or sometimes use a cold finger. So when it deposits differently depending on the flow pattern. So we go through that briefly. This is asphalting. So wax deposition happens because of heat loss. Okay. Asphalting precipitation happens because the change in pressure. Number one. Number two, the change in composition. This means when two oils commingle to each other, we may have asphalting precipitation. When we inject carbon dioxide, it changes the composition, it changes the pressure, we can have asphalting precipitation. There's a picture of the pig. And asphalting is a heavy fraction, mostly aromatic. Okay, so it has a lot of benzene ring and it's a polar thing. So asphalting consists of high molecular weight, polar aromatic. That is asphalting. Wax is N-alkane. Okay, wax, paraffin is N-alkane, mostly N-alkane. Scale is inorganic. Right? Scale requires calcium carbonate scale, so calcium carbonate is inorganic compound. So asphalting precipitation, they can do the test. There's a lab to inject the laser and find out at what pressure that asphalting precipitation happen. Okay, and they can do some quick analysis, spot test, use a paper, drop one oil in. If we don't have anything like this, no precipitation, that's good. If we have the middle one and outside diffuse like this, we may have asphalting. If it becomes like this, we have both asphalting and wax. Okay, this Scale can be sodium, calcium scale. Okay, this is, you know that what scale is. Basically just that we skip the rest. Squeeze. Naphthalate. Before the lunch, let's take a look at naphthalate. So naphthalate happens when crude oil becomes acid. Okay, we can have naphthalate. Let's do the quiz. Put it face down, okay? We will do it together. I forget to mention one thing before we do the quiz, okay? Asphalt precipitate in short NLK. Okay. Asphaltene precipitate in short NLK. But wax dissolve in short NLK. That is the difference between NLK, between asphaltene and wax. So if short NLK is heptane, is short NLK. Short means C7. C7H16 is short NLK. Heptane, hexane, heptane, and heptane. That is short NLK. So when I have short NLK, it dissolves wax, but it makes asphalt into precipitate.
So that's a treatment you can pump and dissolve wax, but it'll precipitate asphalt.
That is how they do the test. When we heat it up, wax will dissolve, will melt, but asphaltene doesn't. So I think I covered everything in the quiz. Then I think you can do it. The last one. So wax dissolve in heptane, but asphaltene doesn't. You can find rest is short. You can find this one. The rest you do it by yourself.
Who I get? Yeah, raise your hand.